about pulleys right now. And we have two different types of pulleys. Okay? We have a fixed pulley and we have a movable. Fixed and a movable. So a fixed pulley, we call it fixed because when you use it, when you actually use it, it doesn't move. It's fixed to a stationary object. Okay? A movable pulley, movable. We call it movable because when you use it, guess what happens? It moves, right? It's a pretty hard terminology. Okay? So first, whenever I draw that symbol means a stationary object. So in this case, it could be like a ceiling, right? Right? So a fixed pulley gets attached to a stationary object. It helps us lift things. So we take a rope, we go up around the pulley, and we come back down. Okay? Now, what does that do for us? Well, I can tell you it doesn't do anything in terms of weight because it has a mechanical advantage of 1. So if it's a 100-pound box, we still have to pull with 100 pounds of force. So it doesn't help us in force. It doesn't help us in distance because we're not giving up either or. They don't have any idea what it does then.
I don't like how you can rotate because you can't let it inside roads.
Exactly. So it changes directions. So now when we pull down, what happens to the box? It goes up, right? So it's changing our function or our direction of that. Okay? A movable pulley, what happens is we have our box, we attach our pulley to our box this time. String comes down and around and goes back up. Okay? Now, when you pull on that string, what moves? The load and the pulley, right? That's why we call it a movable pulley. And what this does is this gives us an actual mechanical advantage of 2. So it makes things twice as easy. Twice as easy. We have to go twice as far, like normal. Okay? So let's talk about the mechanical advantage between 1 and 2. Right? So how do we know it's a mechanical advantage of 1? Well, how many strings are directly attached to that box? Like how many are directly holding up that box? 1, right? So if there's 100 pounds in this box right here, that means that string is feeling 100 pounds of weight on it, right? If this box is 100 pounds, how many strings are directly holding up that box now? There's 2, right? Even though it's one continuous string, there's 2 strands. So each one of those strands has 50 pounds on it. That's why it has a mechanical advantage of 2, because it cuts our force in half. Right? So what happens if we use these things in combination with each other? So let's check this out. So fixed, box, movable, down, and around. So how many strands are directly holding up this box now? 2, 1, 3? What do we think? Like directly holding it up? 2. There's a lot of people saying 2. Right? So 100 pounds box, each string is holding up 50 pounds. So again, this thing is still has a mechanical advantage of 2. So I'm going to give you a little tip. Actually 2 little tips. Number 1, to find mechanical advantage of a pulley system, what you're going to do is you're going to count the number of supporting strands. Number of supporting strands. And what a supporting strand is it's a rope, string, cable, doesn't really matter. Something that's directly holding it up. So those two strands right there are directly responsible for holding that box up. Okay? Is this strand out here, is this thing directly responsible for holding that up? No. So it's not like directly holding it, okay? It's not directly holding it. It's there. If I let go, what's going to happen to that box? It's going to fall, right? So we are responsible, but we're not directly responsible for it. Meaning we're not supporting it exactly in the direction it's trying to go. Okay? So here's my other tip. I can't tell you up, down, left, or right. Okay? But what I can tell you is if the arrow is going towards the load, it's going toward the load, you're not going to count it. Don't count it. So if it's going towards the load, you don't count it. And if it's going away from the load, what do you think you do? Yeah, you count it. I'm going to show you two different versions here. So if it's going towards the load, you don't count it. Going away from the load, you do count it. So you're going to count everything else, and then where the arrow is, you're going to make a decision. So let me give you two examples of how this works. So we have two fixed pulleys, two movables. So we have that. And we have that. Same amount of pulleys, but the arrows are going different directions because depending on where we start, if you notice, we started here at the top, we started on the bottom on the right side. So here's what I do. I cut through all of them. Cut through where there's the most, and I'm going to count everything I cut through, and on the one I get to the arrow, I'm going to make a decision about. So I get 1, 2, 3, 4. So I've cut through 4 strands that are directly supporting it, and then the arrow is going towards the load or away from the load. It's going towards. So do we count it or not count it? Don't count it. So our mechanical advantage is what? 4. Mechanical advantage of 4. We can do the same thing over here. Everything we cut through that doesn't have an arrow on it, we count. 1, 2, 3, 4. Cutting through the arrow. Which way is the arrow going? Is it going away or towards? Going away from the load. So do we count it? Yes. So this one has a mechanical advantage of 5. So some people ask, like right off the bat, why don't you just tell us up or down, Mr. Bernstein? Why don't you just say, like, if it's going down, we don't count it. If it's going up, you count it, because that seems like it's pretty universal. The problem is we don't have to use pulleys vertically. We can use them horizontally, like tow truck drivers, we said a couple of days ago. They can use them horizontally. So your up and down scenario doesn't work, right? Now, that give and take relationship still exists. So on the right hand side here, we have 5 times 5 mechanical advantage. So this box weighs 100 pounds. What's 100 divided by 5? We get 20. So I only have to exert 20 pounds to actually lift that 100-pound box up. That's pretty impressive. But what do I give up? I give up distance. So where does that distance come into play? Do you have any guesses?
What do you mean by that?
So if I want to lift the box up 1 foot, I need to give up distance somewhere. I actually have to give up 5 times the distance.
Well, it's like in a string. Like if you're pulling the string, you're gonna have to pull 5 times more.
Right. So let's show what he just said there. We'll do an easier scenario. So let's label all of our variables. Do we all agree that the 100 pounds is FR? Do we agree on that? Yeah. Our 100 pounds is our FR. Our load is 100 pounds, that's our FR. Our load is always our FR. Where's our FE? Kind of alluded to it on the last picture. Right, so where my arrow is, that's my FE. So here's my FE. Alright. Here's my FE. Where's my DE and where's my DR? These are the ones that get a little confusing. So you kind of alluded to it, right? You said, well, how much you pull is your DE. So that distance that you pull is your DE. Pretty helpful. Where's my DR?
It's the distance from like the weight to the top.
Not to the ceiling. I mean, I guess you could represent it somehow like that. I do this. It's how far you lift. It's how far that box moves. So the DR is how far the box moves upward. DE is how much you have to pull. So let's take a look at this. If this is a 100-pound box, what's the mechanical advantage of the system? What do you think of this? 2. A couple of you saying 2. So mechanical advantage of 2. So if I want to find FE, I have mechanical advantage of 2. I have FR, which is 100. I want to find FE. Do we have a formula that has FR, FE, and a mechanical advantage? Yes. Actual mechanical advantage. So AMA equals FR over FE. So we get 2 equals 100 over FE. We do our multiplication and our division. Multiply both sides by FE, which cancel out. We have FE times 2 equals 100. Now what? Divide both sides by 2. So we get FE equals what? 50 pounds. Some of you were thinking, I could have done that in my head. I already knew that. Right? That's the way you can do it if you don't know how to do it in your head. Okay? So each one of those strings has 50 pounds on it. You're connected to one of those strings. So you're 50 pounds. So the question I have for you guys is, if I want to lift the box up, let's say 5 feet. If I want to lift the box up 5 feet, how much rope do I need to pull? I have to pull twice as much. So I want to lift 5, so I have to pull 10. I have to pull 10 feet. You're not sure how we did it? You can go Mechanical advantage equals 2. dr is 5. de is, we all know. Do we have a formula that has de, dr, and mechanical advantage in it? IMA, right? So IMA de over dr. We get 2 equals de over dr, which is 5. 2 times 5, 10. We get 10 feet. Is D, sorry. All right? Here's the point. Does your IMA formula work? Yeah. Does your AMA formula work? Does your static equilibrium formula work? Yeah, absolutely. Okay? Those 3 formulas all work. They still work, so continue to use them. Right? How do you calculate mechanical advantage of a pulley system? Count all the supporting strings, right? And the rule of thumb is if the arrow is going towards the load, don't count it. And if the arrow is going away from the load, you count it. Okay? Question.